Hey, welcome. Today we're going to learn about something called thermodynamics, which is pretty hot.
Yeah, or maybe not.
A little bit. So one of the big things with thermodynamics is you have this thing called the first law of thermodynamics. There's more than just one law, but the first one is the one we are most concerned with, especially in terms of the scope of our course. So without further ado, here we go.
Let's do this.
So the big thing is you already know about the main idea of thermodynamics in the sense that you can't really destroy energy and stuff like that.
Nope.
But in thermodynamics, the environment of a chemical reaction is separated into two parts.
Okay.
So there's two separate pieces that go with it, and the first one is called the system, and the second one is called the surroundings.
Okay.
So the system is usually the thing that we're going to actually be studying. In our case, since it's chemistry, it's going to be the chemical reaction.
Okay.
And then the surroundings is literally everything else.
The room that it's in, the air or the gases that surround it, everything.
Yep, everything.
Okay.
It could be a duck walking past.
The container that it's in.
Yep.
That. Okay, cool.
Any of that type of stuff's going to work. So, as an example, if we look at something called a piston, now you've probably all heard of pistons before, I hope.
Car engines.
Right. There's a very basic reaction that we could talk about, but this one here is just in general is reacting hydrogen with oxygen to make water.
Cool.
And it releases a ton of energy. So, the big thing with this in this piston, if you look at this awesome drawing that I drew.
That is awesome, by the way.
I'm sad to say that I drew that myself.
It's a photo, isn't it?
Yeah. Well, the one is, but then I drew the little molecules. So, anyways, mass is not gained or lost, so mass is staying constant. And there's no exchange of matter that happens. So as a result, the only thing that can be exchanged with that in the environment is heat or work.
Okay.
All right? So we call this a closed system.
Oh, so it weighs the same before and after.
True.
If you literally weighed it, you would still get the same numbers on their thing. And you're calling it a closed system because it doesn't interact with the environment in a way that actually exchanges matter.
Right.
Again, conserving it, and that says it's a closed system. I got it.
Yep. So there's other things like open systems where then you have to include the idea that matter is being exchanged, but we're not going to deal with that for right now.
Okay.
So basically the idea is that systems, they try to get to as low of an energy as possible, as low of an energy state as they possibly can.
Hooray for entropy.
They usually are going to get rid of it. And an easy example would be like this little guy who's trying to run away from it.
That little guy is awesome.
Oh, he's freaking amazing. He's what
Indiana Jones beats Han Solo any day. And I will debate that.
I'm with you.
Indy rules.
So, Mr. Harkins, can you explain why this is an example of law of thermodynamics? Or closed versus surrounding systems?
Yeah, well, if we're talking about on here is things tending to get as low energy as possible, tending towards entropy. What you've got here is you've got a boulder rolling downhill, chasing the incredibly awesome Dr. Indiana Jones, and eventually that is going to run out of kinetic energy.
Yep.
And it's going to stop moving. And it's going to have much lower potential energy than it started as well.
Very true.
So
starts up high, lots of energy, ends down low. Well, starts up high, ends low.
Yeah.
Basic idea.
Yep.
In terms of chemistry, an example of that would just be like in a chemical reaction, you start with a high potential energy and it wants to go towards a low one. Basically, you get your reaction that happens.
Yep.
The whole idea is going on.
All right, so let's talk about the law of conservation of energy. And it's just like what the name implies. It says that energy isn't created or destroyed. It is conserved. And the cool thing about this is that it ties in exactly to what this entire little video is about, which is the law of thermodynamics. And if you take a look there, it says the total energy that you gain by a system equals that's lost. So you got some coming in, you got some coming out, and vice versa. If you lose some out, then you're going to gain some. It conserves that energy at all points, and that is the law of thermodynamics, not a theory.
So is it
the real deal?
So what you're saying is it's not possible for me to have a reaction start with a certain amount of energy we put into it, and at the end I somehow magically get lots of extra energy that's from nowhere?
Nope. You can't make matter out of nothing. You can't make energy out of nothing. You're not going to have that. It will be conserved.
So like a perpetual motion machine?
Impossible.
Oh, damn it.
Impossible. At least according to our current laws of the universe. Different dimensions? Who knows?
Well, maybe we'll work on that. So. Cool. So this is a big deal, though, obviously.
Oh, gigantic. It drives the entire universe.
Everything we kind of deal with in terms of chemistry, up to this point, we have not really talked about the energy aspect. We talked about chemical reactions and how they work. You guys know how to predict products and all that kind of great, awesome stuff. But we've not talked about what actually drives it. And what drives it is energy. Energy is the king of everything. Not enough energy, you got nothing.
It's the kick in the pants from nature.
So we're looking really at this thing called internal energy.
Okay.
And the internal energy is basically just the sum total of all the energy of the system.
Okay.
Regardless of the type. We're talking potential and kinetic here.
Okay, so it's both of those together. We're going to call it capital E is going to be our variable we're going to use for this guy. Okay.
So we're including everything here. We got the motion of the molecules, the motion or potential energy of the nuclei, the electrons.
So everything inside the atoms, we're talking all motion, all kinetic,
Yes.
All potential.
Everything down to the smallest little piece that we can possibly get to. That is all included in it. So what you get is this little delta E. Delta E stands for change. And it's literally just the change in the internal energy of a chemical system. Now, it's a very, very hard, very, very complicated equation.
I am not going to remember
ready
this
for
because
this?
math is hard.
There it is.
What?
I know.
Okay.
Watch out now. Delta E is
There's a
equal to
minus
E final
sign in there. Oh.
minus E initial. Now, I know it's hard. You got to think the start versus the end.
So the change is just a subtraction thing.
Exactly. Not too tough.
I'm going to write it down.
But in terms of chemical reactions, where do you think the final energy is going to be found? In the reactants or the products?
Oh, final energy's got to be in the products. Is what you produce.
You win the prize.
Woohoo! Can I go home now?
Yes.
Yes.
All right, come back.
I got bored. I want to come back. I don't have anything going on at home.
Yay. I have friends. See, I told you guys I do have friends. You don't believe me, but I do.
You paid me $2.
Right. Hey, even though I paid you, you're still
Yeah.
here. All right.
Yeah.
So there's two other big terms. We got endothermic versus exothermic, and most of us are pretty familiar with that.
Yeah.
But in terms of energy of a system, we're still looking at change. And the big idea behind this is endothermic is when you have more energy at the end, like into your system, than you had at the beginning. You have an endothermic reaction.
Positive value.
Right, because you've absorbed that energy.
So you've
from the
got
surroundings.
a quote-unquote gain of energy there, which isn't really a gain. It's more like...
Right, well, it is. It's like it's what was not in the chemicals beforehand.
Okay.
Absorbed from the surroundings. Now, the big
There
thing
we
that's
go.
weird with that is people are like, wait a second, didn't you a second ago say you can't have random energy built in?
So what's the caveat there? What's the difference?
Well, the difference is you have to know that the energy was there. It just wasn't in the chemicals yet. It was in the surroundings.
So it's not,
exactly.
So we're pulling it from the environment around. So again, we're not just creating energy. You're gaining it, but not
From
creating
something
it.
else.
You're drawing it from the environment around your system.
Right. So
Neat.
if my system has absorbed energy, that means the surroundings has...
Have lost it.
You got it.
So they lose it, you gain it, and that's the gain-loss. So what you're saying then is if my system gains energy, it's endothermic, and we'll get a positive value.
Yep.
Conversely, if my system loses it to the environment surrounding it, then I'm going to have an exothermic.
Exactly.
And that'll be if one was positive, it'll be negative.
True.
Yes.
So remember,
I'll rock this test.
Positive E, endothermic. Negative E,
I'll
exothermic.
definitely write that shortcut down.
True. So, as an example, if we look at something like this, where you have zinc reacting with hydrochloric acid, you're going to form zinc chloride and hydrogen gas. And energy. See, this is the new piece to us. We got this plus energy part.
So, but energy's not a chemical, right?
No, but we have to include it in the reaction because we're dealing with it. Before, we could leave it off because we were just concerned with the rearrangement of matter.
Yeah.
Now we're looking at what's going
Both
on with the energy
components.
itself.
Okay.
So imagine that your energy initially is 1,750 joules.
That's what we start with.
And now that's built up in the molecules, the bonds within them, all that stuff.
All
is
the
built in there,
vibrations,
movements.
everything.
Yep.
Okay.
At the end of the reaction, you have 1,250 joules.
So we lost some. It's
Right. Now the
lower
big thing
value.
here is you got to remember that those values, I almost like pointed at like you guys can see
Yeah.
it, but the value,
like
that
those.
1,250 joules is in those molecules.
Okay.
That's what's in the molecules. The other energy is where it says energy.
Oh, so we are accounting for all that, as you said in the beginning.
Right.
And
So-
we can figure out how much is in there, can't we? Just by doing that very
Simple
difficult
math.
formula.
I know. Get out your calculators.
So so it's final 1250 joules minus the initial, what we started with 1750, which means we have a negative value on that. And if we've got a negative value,
Is it going to be?
it's going to be exo,
exothermic.
right?
So, not too tough.
No, I
Now,
got
what
that.
happens though if we switch the arrow around?
Chaos.
Okay, now don't blink because you're going to miss it.
Look
Here
at it.
comes. Ooh.
That was awesome.
So if I switch the arrow, though, we have to switch some of these numbers around. Or
Yep.
at least not numbers, we have to switch around the values. Because now our EI and EF has changed.
Yep. So we
Okay, so yeah, we had to switch the symbols around.
Okay.
EI, EF, because we switched, now the initial is over by the zinc chloride instead of
that's
by
what
the
we're starting with.
hydrochloric
We're
acid.
driving your
But you're still going to end up with the same basic calculation.
yeah.
Final minus initial.
But now the symbol on it's going to change. So
it's
now we have a
hot.
positive. So we now have a positive 500 joules on there for the delta E.
So what is it?
Oh my gosh!
Endo
So
or
if the
exo?
one was exo and it's negative, this has got to be endo.
True.
Woo!
I knew I had you
I am
for a reason.
Woo!
Yes. I done taught you well.
Yeah, I'm learning me some chemistry.
So if we want to relate delta E to heat and work, which is something we've talked about before, we have another equation. We
Let's
have this
apply
Q
that
plus
energy.
W thing. And Q is the heat added to or given off by the system, which is not too hard to think of.
Nope.
Work is what the work being done on the system or being done by the system. And we talked about work before, so just think about you could have an expansion of gas expanding and pushing against a container. Could be work being done on it. Maybe you apply pressure and you put work into it.
All those things. Boilers, any of these kinds of things. Any system that you're going to have.
That's how a piston works.
Piston
pushes it up. Basically, this is an algebraic expression of that first law.
Because
now we're actually looking at heat and work, adding it all kind of into each other. So if you add heat to a system, you're positive. If you take heat away, it's negative.
Okay.
So if you put the heat in, it's positive. If you release it, it's negative. And the same exact thing works for work, which is kind of nice.
Yeah, it's nice so it's a direct relationship between the two.
So, quick example. If a system absorbs 50 joules of heat and does 10 joules of work, what would be the delta E? So, Mr. Harkins, what would you need to do?
So it says it absorbs 50 joules of heat. So our heat is going to be, let me see, absorbing, that's going to be a negative.
It's going in, so it's going to be
it's going to be positive.
There you go.
Okay.
It's all right.
And it does 10 joules of work, so that's going to be our negative.
There you go.
Yeah.
So the Q is...
I was thinking about it backwards. So yeah, it does take a little bit to think about these things and make sure you got
a little odd.
Especially when I can't look at my equation. I'm old, I forget.
So you got Q plus W.
Yep.
So like you said, 50 joules.
Positive 50 joules in makes it positive. And you're doing the work, so it's plus a negative 10 joules, which is going to end up with a boon or a positive of 40 joules.
Ooh.
Making it, if it's going to be positive, it's going to be endothermic.
You got it.
Yeah.
So overall, this is an endothermic event.
Yeah.
Since we
whatever
don't
it
know
happens to be. Yeah.
Exactly.
Whatever it happens to be. But putting these numbers on that event says that is going to be positive. It pulled 40 joules out of the environment around it.
All right. Let's see if you guys can do it on your own. So here's your setup. Ready? Calculate the delta E for a process in which the system absorbs 65 joules of heat and receives, or absorbs also, 12 joules of work from the surroundings.
Okay, I'm going to get my paper.
Okay, ready? Go. All right, hopefully you got it. If not, well, here's the answer. Hopefully you found it to be positive 77 joules, making it endothermic.
Yep. If you didn't work through that, take a shot at it. Make sure this stuff makes sense in your head. Doing it once, save you a lot of work later.
True dat, and we'll go through more stuff in class.
Very cool.
Questions?
Nope, all good. I'm going home to work on these things now.
Peace. Bye.